Okay, this is paper 2, part 2, the 5th of the videos out of 6, where I'm doing the sort of medium difficulty questions from paper 2. Funny enough, it's all the section B questions that fit in this category. You'll notice that some of the questions are actually quite easy. They could have been in the first video, but I choose to do whole questions rather than sub-questions in each section. So this goes from easy to medium difficulty. Also, the content in this video is a total of a whopping 50 extra marks. So it means that if you can do the contents of the first video and the second video, you're up to already 88 marks out of a possible 110, which is definitely the level you'd be at to make a grade 6 at the exam. So you'll notice that in this case, the paper 2 was generally a bit easier than the paper 1. Of course, there were difficult questions for the next video, but they were considerably less of those. So let's hit it up with question 10. Ta-da! So, as I did in the paper 1 videos, since this is section B and it says very clearly on top of the page that we are not supposed to write solutions on the page in the question booklet, then I have uploaded a more or less genuine answer booklet into my little notebook, so I can write exactly in the way that you would be working at the exam. So I'll start by filling out neatly my name and very clearly marking which question we are currently working on, which is question 10. So question 10 you have down here on the left. Happy review with this little thing that hangs in a spring and bounces up and down, and the height measured in meters is given by this function h of t. And you'll recognize that h of t is a cosine function with these usual transformations of the graph, that we have a number 7.8 multiplied on the variable t, and then we have an amplitude a multiplied after the cosine, and we have this average value b added to it. So we can already start imagining how all these work on the graph, except that, of course, we don't know the value of a and b yet. Anyway, question A asks us to find the period of the function, and you kind of need to memorize that period has everything to do with this number 7.8 that we multiply on t, because multiplying with the number in here before the cosine is going to squeeze the graph and make the period become shorter. So if the number is 1, then the period is 2 pi, and if the number is larger, then whatever number that is, the period is going to be 2 pi divided with this number, because these horizontal transformations, they work sort of the opposite way that we imagine. If we multiply by 7.8, in there we're not stretching the graph, we are sort of squeezing the graph by a factor 7.8. So for question A, it's really just a matter of saying that the period t is equal to 2 pi divided by 7.8. And of course, since this is paper 2, we're going to call up the calculator. Oh, that worked. Wonderful. And ask what 2 multiplied with pi, where is goddamn pi? I can't find pi. So that's 3.1416. And divided with 7.8. You will want to locate pi on your calculators and look less ridiculous than I'm doing right now, but this works for now. So this is approximately equal to 0.806, rounded to 3 significant figures, as we are supposed to do. moving on. I found pi now. It's, if you follow my cursor, it's up here on the blue button with this one. Anyway, that's for another time. Anyway, going back to the questions and moving to the next page. Oh, I'm trying to do quite a lot of things at the same time. So here is the second part of question 10. Now, we release the weight and it starts bouncing up and down as it's supposed to, and the graph of h of t looks as you can see on the paper. And of course, they're going to ask us now, judging from this graph, what is the value of a and b? So the easiest one here is actually b, because b was, and I'm trying to go back up. If you look up here, b is the constant that we're adding to the function, which sort of just lifts the cosine graph to have an average value of b. So we are supposed to look at this graph and find out what the average value is, like around here, that we oscillate around is. Now, it's really hard to just read on the graph, so we need more solid information. And it says up here that the maximum height is 1.8 meters. So it means that the maximum is in the y-coordinate 1.8. Matches fairly nicely with what we can see on the graph. And the minimum height is exactly 1 meter, as we can see here. So the average value is also called the average value because it's the average between the maximum and the minimum. So b is equal to 1.8 plus 1 divided by 2, and we don't need the calculator for that. That's going to be 1.4, I suppose, half of 2.8. So that's for b. Now a, if we go back, is the number that we multiply on the cosine. Oh, here comes a helicopter. I don't know if you can hear that. Just flew by my window. A is the amplitude. The number we multiply on the cosine sort of stretches the graph vertically and makes for a higher variation around the average value. And to find that, we sort of just need to see how much this oscillates away from the medium value. However, we have to be a bit careful, because it's tempting to say that A is, you can just say, what's the difference between the maximum and the minimum? I'm going to do that, 1.8 minus 1, and then divide that with 2, because that gives us the size of the oscillation away from the average value. And that, of course, is going to be 0.4. But that will give you one of the two possible marks in this question, because it's actually wrong. The method is fine, but in order to actually get the actual real result, you have to realize one more thing, that if you look at this graph, it's actually not a cosine graph, because a cosine graph will always start when t is 0, it will start in a maximum, and this guy starts in a minimum. So either what we have done is doing a phase shift to the left or the right, but that's not happening here, because if you look at the function, there is no phase shift. It would be a plus inside the cosine bracket. So the only other way to explain it is that we have actually had an amplitude that is negative. When you multiply with a negative number, you still stretch the graph, but you also flip it vertically around the mean value. So if a is negative, then the graph will start in a minimum. So in fact, what we have found here is the absolute value of a, which is correct, but since h of 0 is a minimum, we can conclude that a is actually equal to minus 0.4. And that's how to get the other mark in this question. Question C, let's move this up here. Question C asks us to find the number of times that the weight reaches the maximum height in the first 5 seconds of motion. And what you can think there is that you just start by calculating how many periods we go through in the first 5 seconds. So you can calculate that by just saying what is number of periods by taking 5 and dividing with the period. And for that, we of course pull up the calculator and we say 5 divided with 0.806. That gives us approximately 6.20. However, you have to be a little bit careful with the rounding here, because going through 6 periods can actually give you, it will definitely give you at least 6 times the maximum value, but it can also give you 7 if you start in a maximum and you finish in a maximum. And if you go through a little bit more than 6 periods, like 6.2, it's quite likely that you will start just before a maximum, and then you'll actually manage to do 7 whole maxima, even though you're not doing 7 whole periods. So it's really good that if you look at the graph, you realize that we actually start in a minimum, and they are saying the first 5 seconds, so it means that we are starting at time 0. So therefore, it is quite safe to say that we are already spending 1 half period, which is like approximately 0.4 seconds, in order to reach the first maximum. Then there's less than 6 seconds left. So we can be absolutely sure that we don't make it to have 7 times a maximum. So number of maximum is 6 times. And you can argue, say, since we start in minimum, in order to have 7 times maximum, you would need at least this number 6.2 to have been 6.403, like having half a period more. But it's not. So that's the answer to C. Now in D, they want us to find the first time that the base of the weight, which is the one that we're looking at the position of, reaches a height of 1.5 meters. So D is really just saying we have to find the value of t such that h of t is equal to 1.5. So no trickiness there. However, this equation as such has infinitely many solutions, and we need to be careful to find the first one. And if this was paper 1, we would be like super stressed and confused about how to make sure we find the first one and all that. But this is paper 2. So what we do is we plot the graph. Let's clear this. And what do we have? We have the A that was minus 0.4 times the, oh, I just used the wrong minus. Minus 0.4 times the cosine of, and I just need to look at the function, 7.8. 7.8 times the variable, I need to call it x when I speak to the calculator, and plus the b value, which is 1.4. Enter. And before I go on, I go and check that we're working in radians, because otherwise the graph is going to look weird. And we are. So we can safely say that I want a window with x values. I don't need minus 10 because we don't get negative values, but I need to go to, where is the graph? Well, I also just need to go to a height of 3. And, sorry, that was the y. So let's go to the y. -1 and 3. And then we go to the x's. What do we need there? -1 is fine. And then we need to go all the way to, so we need the first 5 seconds. So let's just go to 6. And let's do the graph. It looks like this. Starts in a minimum as it's supposed to, and does a little bit more than the 6 maxima because we went a little bit further than 5 seconds. And we have to find the first time that we get to the height of 1.5. So a good idea is to just go and say, well, I need another line where y is equal to 1.5. And we do that graph. And then we go to the calculate menu and look for intersections. So press 5. And for the first curve, we just choose the one they suggest. For the second curve, suggest the other one, surprisingly. And then for the guess, we have to go somewhere close to the actual intersection that we want to find. It doesn't have to be super accurate, just closer than it is to the other intersections. And there we go. Here is the solutions. So we're going to write that using graphical display calculator, we get the solution that t is approximately 0.23 and 4 seconds. So, in fact, since I know that I'm going to need this result for further calculations, I actually want to save a few extra digits. And I'm actually going to do that on the next page to say that t is actually equal to 0.233779. Well, that's plenty. A bit further precision in order to avoid rounding errors piling up on each other. Because question E is where it gets confusing. Now they set up a camera to take a picture of the weight that is bouncing up and down at a random time during the first 5 seconds of its motion. And this is a rare case of a question that will get harder for you when we have covered the next year's curriculum. The explanation is that in 1 year from now, you will read this and then you will be really confused because what does random time actually mean? What I'm going to teach you over the next year is that there are many ways of having a random time in the first 5 seconds because you can have different so-called probability distributions. And the right question to ask here for the poor people who are at the exam would be like, with what probability distribution is this randomness? What is the randomness actually defined as? And the answer that you're supposed to realize yourself is that since they don't say anything about that, then they are kind of working on the second eye sort of thinking level, where random means what we will later on call uniform probability distribution, meaning that every single interval of the same length has the same probability of being the interval in which we take the picture. So like all times are equally likely to be the time where we fire the camera. And this is also the intuitive approach, but as I said, in the next year, I'll teach you that it's not always the actual way you need to think. But in this case, since we don't have any further information, we simply assume that it's with a uniform probability distribution. So in fact, they fire this camera at a time during the first 5 seconds, and all times are equally likely, and they ask us to find the probability that when the picture is taken, the height of the base of the weight, the height that we're looking at, is larger than 1.5 meters. And then we kind of need to look at the graph. And if you can see my cursor, what we have is that we found sort of the first time around here, I don't know how to make it an arrow, but the first time that it reaches a height of 1.5. And notice that then it stays above 1.5 for an amount of time. And wouldn't it be interesting to find out how long that time is? For that, we're going to need the second time we reach this. And since we have the thing in the calculator, it's very easy to just go and say, well, I also need to calculate. So press 5 again. Another intersection with the same two curves, but now I'm moving my guess over here. And then the second intersection is when t is approximately 0.571, and I'm again taking plenty of digits because this is not what they're asking for, 757. So if we subtract these two times from each other, then we get the duration of the time interval where we are above 1.5 meters. So I'm going to start doing that. So I'm going to take this 0.57. Oh, sorry. I am going to quit this, and then I'm going to say my number 0.571757 minus 0.233779 with plenty of digits to see that the duration above, oh, by the way, this is question 10 still, and I'm now working on sub-question E. Duration above is the difference between these 0.337978 seconds. That's the time interval where we are above 1.5 meters the first time. But since we're looking at the first 5 seconds, so out until approximately here, we have more. And how many times do we have this? Well, we definitely have 1, 2, 3, 4, 5, and 6, since we are going through a little bit more than 6 periods. And we know that we are definitely moving to here, which is 6 whole periods. But as we answered in question C, we go a little bit more. And then you'll have to worry if this little bit more that we go to the right actually gives us a little bit more time above 1.5 meters. But it doesn't, because if you remember, we were having 6.2 periods, so less than 6.25. So we don't even have an extra quarter period. So what we're going is less than going to where we would have the average value that is smaller than 1.5 anyway. So t equals 5 is somewhere around where the cursor is pointing right now. So definitely there is only these 6 peaks that go above 1.5. So we can simply say this we take times 6, and that's easy to do on the calculator because we have the result here, which is multiplied by 6. And that's going to be 2.027868 seconds in total. And then for the very naive way of calculating probabilities, the probability of landing in one of these time intervals is the total number of seconds that these time intervals are, that's the number we have here, divided with the total length of the interval. So the probability is simply this number, 2.028. I can just round it off here and use all the digits actually, divided by 5 seconds, which of course I do on the calculator by just saying this number divided by 5. and that's 0.406. And that's a final result. So I'm rounding it to 3 significant figures, and that's the probability. Moving on to question 11, we remember that you're not supposed to start a new question on the same page as you have answers to a previous question. So we skip to a blank page in the answer booklet and write now it's question 11. Question 11 gives us a function that is this lovely, it's called a rational function if you have a polynomial divided by another polynomial, defined for all values of x except when x is -3, because in that case we get to divide by 0. And A asks us to state the equation of the vertical asymptote on the graph of f. And just like in paper 1, a vertical asymptote happens only in values of x where the function is not defined, and there is only one such value, so it's really straightforward. And since it says the word state, it means that we don't even have to argue. It also, I think it's only a 1-mark question, so it's just right or not right. So we are just supposed to say that the equation for the vertical asymptote is exactly that x is -3. Done. Question B says find the coordinates of the points where the graph crosses the x-axis. So to cross the x-axis, we need to have a function value that is 0. So we're going to ask f of x, for which values of x do we get the value 0? And since f of x is a fraction can only be 0 if the numerator, the one on top, is 0. So we can actually just focus on the question, when is x squared minus 14 times x plus 24 equal to 0? And what do you know? That's just a quadratic equation. So how about just solving it? I'm going to finish the square. X minus 7 squared, that's half of 14, minus 7 squared, that is 49, plus 24 equals 0. And I guess 49 minus 24, so x minus 7 squared is 25, which is really nice. It means that x is equal to 7 plus or minus the square root of 25, that is 5. So x is either 2 or x is 12. However, they ask for the coordinates in plural, so these are the x coordinates. We also need to calculate the y coordinates. But then again, since we are intersecting the x-axis, the y coordinates are going to be 0, because that's what we just asked them for. Otherwise, we would just put the x coordinates into the function and see what it is. But we've started this whole thing by saying that it has to be 0. So of course it is. So intersections points are 2, 0, and 12, 0. There we go. Then the graph of f also has an oblique asymptote. That's the ones that are neither vertical or horizontal. So it has an equation of the form y equals ax plus b, where a and b are rational numbers, and we have to find those. So how is it with finding oblique asymptotes? Well, they happen precisely when you have a division between two polynomials where the top polynomial has degree 1 larger than the denominator polynomial. And the way to find it is to do what we get to do far too rarely. So finally we get permission to do polynomial division. So we're actually doing the division, saying 2x plus 6. How many times does that divide? And I'm doing it my way, even though it annoys some of you. Oh, shit. That was not the intent. Even though it annoys many of you. How many times does this divide x squared minus 14x plus 24. First of all, how many times does 2x divide x squared? Well, it has to be multiplied with 1/2 times x. And when you multiply 1/2 times x on the divisor, we get x squared as we wanted, and we also get plus 3x. And then we take the difference, we subtract this from what's above, and what remains is actually minus 17x, and we still have the plus 24. So again, we ask how many times does the divisor divide the remainder that we have here, and the answer is minus 17 over 2, because when we multiply 17 over 2 on this with a minus, we get minus 17x. And then we get minus, so 17 times 3, that's 51. Right? And of course, the remainder is then, it doesn't really matter much, but let's just find it. These cancel out, and these become 75. And the upshot is that f of x is equal to 2x plus 6 times 1/2. Wait a minute. 1/2 x minus 17 over 2 plus the remainder. I'm going to write this nicely. Sorry, let's just do this. So the conclusion on a polynomial division is that f of x, you can replace the numerator, which was this x squared minus 14x, you can actually replace it with 2x plus 6 times 1/2 x minus 17 over 2 plus the remainder, that is 75. And of course, this is still divided with 2x plus 6. And the nice thing is here that 2x plus 6 divides into both terms, and the first term, it just removes this. So we get 1/2 x minus 17 over 2, and then plus the 75 over 2x plus 6. And the whole idea is that this shit out here disappears when x goes to plus or minus infinity, because it's just 75 divided with something that becomes infinitely big. So that means that the stuff here is approximately the function value when x goes to plus or minus infinity. And that means that what we have here is actually the equation of the oblique asymptote. So that means that the a is equal to 1/2 and the b is equal to minus 17 over 2. And they are nicely rational numbers, as they're supposed to be. Question D. Still working on question 11, and sub-question D says that we have to sketch the graph of f for x between minus 50 and 50, showing clearly the asymptotes and intersections with the x-axis. So we need the work that we did on the previous page, and of course I am not going to be on paper 2 and not using my calculator. So we go to the calculator, we clear the definitions from before, and then we type in the function. So let's see if I can do this. I can. We have x squared minus 14 times x. Oh, that didn't work. X bracket x squared, right, minus 14 times x plus 24 bracket divided with bracket 2 times x plus 6. That's my function. Window, well, the x-coordinates I want is between minus 50 and 50. So I'm going minus 50 and 50 here. The y-coordinates are a bit harder because we don't really know. So let's just say, let's start out with the default minus 10 to 10, and then we can always change our minds when we see the graph. So let's draw the graph. There it is. And what we can see here is that it seems that there is only a graph on the right side, and that is because the function values out here, they are sort of too small to be in the window. So I need smaller values of y. So maybe I'm going to do minus 30 instead. See if that helps. There it is. And there it is. So this is the graph that we want to draw. Let's do a large coordinate system. And put some arrows on the axis. Say this is minus 50. And out here is 50. And the graph looks like, well, let's do the asymptote first. The asymptote was when x was minus 3, and this is the vertical asymptote right there. That is x equals minus 3, and that one is showing very clearly. And then the graph does something like going to minus infinity, then swooping around. They didn't ask us to find the location of the local maximum, and then starts going downwards. And it becomes more or less linear because it's going to follow the graph. Maybe a little bit more like this, because we also want to have the oblique asymptote, which was something like it has an intersection with the y-axis around minus 17 over 2. So that's around minus 8. So it's going to be around here, minus 17 over 2, which is where the oblique asymptote sort of touches the graph. Let's do like this. And then fix it up. That's y equals half x minus 17 over 2. Showing clearly. And then I need to fix my graph because it doesn't go away from the asymptote. It goes towards the asymptote. There. And on the other side, it comes from up here, going down. It actually crosses the y-axis and starts going up towards the asymptote. And this is what we found to be the x-coordinate 2, and this is the x-coordinate 12. And that's sort of as well as we can do. Let's just check. Did we sketch the graph? Did we clearly show the asymptotes and any intersections with the axis? Well, no. We need the intersection with the y-axis that they didn't ask for. So let's just calculate f of 0 that we haven't calculated yet. That's pretty nice because that's just 24 over 6. So that's 4. So up here it says 4. And that's kind of all they could ask for. Question E says, find the range of the function. Oh, how nice. So we look at the graph that we just drew so neatly, and remember that the range is the set of all the y coordinates for the points on the graph. It's all the values that the function makes. And in order to find that, we can kind of see that it would matter to find this local maximum and this local minimum. And thankfully, we are on paper 2. So we go to the calculator, turn it back on, and say, now I want to calculate the maximum. So I press 4. And I'll just adjust the left bound, put it around here, and the right bound on the other side of the maximum, and the guess somewhere in the middle, and it's swooping. So we have local max. And notice that what we need is actually the y coordinate. So the y coordinate is when y is equal to minus 18.66025. Sorry, I said 6. Stop. 6025. And similarly, we're going to find the minimum. So calculate. Now I press 3. And we go around here. The left side. Right side. Somewhere in the middle. And there's the minimum. Local minimum is when y is minus 1.339746. So that is all we need, because if you look at the graph, the range so by the way, we have to write this is question E we're answering. The range goes from minus infinity, sorry, we are in the, like this, minus infinity to this local maximum value, which is minus 18.66. Well, 3 significant figures, 18.7, and this one is included because we actually get that value. And then you can use this symbol to say also united with the values from minus 1.34 all the way to infinity. And that's the beautiful range of our function. Finally, question F tells us to solve the inequality where f of x is larger than x. And for that, we need to compare the graph where we can see the y-coordinates of f of x to the y-coordinates that are equal to x. So it's tempting to just go to this graph and say, now I'm putting in an extra function where y is just equal to x. And we put that on the graph. And it looks like this. What you can kind of tell is that since the oblique asymptote has a slope of 1/2, we can kind of see that what happens, if you can see my cursor, to the left side is that the graph of f is going to stay higher than the straight line y equals x, because it has a lower gradient. So this one goes down faster. And similarly, on this side, after the intersection, we can also tell that this one is going to increase faster than this guy, because this one approaches something with a slope of 1/2. So if I want to know for which values f of x is larger than x, I sort of realize that we have to find the places where they are equal to each other. That's here and here. And we do that with the calculator. And we press 5 for intersection, first curve, second curve. And I'm going to guess somewhere down here. So for f of x equals x, and I use the GDC for that. That's when x is approximately minus 21 0.1, or I'm also going to find the other one, calculate 5 intersection, first curve, second curve, and then somewhere out here, when x is approximately 1.14, rounded to 3 significant figures. And as you can see on the graph, when f of x has to be larger than, so f of x can only swap to the other side of this line in two different ways, either by intersecting the line or by having a vertical asymptote, because then it can sort of zoom from minus infinity to plus infinity. And that's exactly what it does. So the values of x, where f of x is the larger one, is x being smaller than minus 21.1. That's out here to the left. And then it becomes smaller for a while until we reach the vertical asymptote. Or minus 3 is smaller than x. And when does that end? Well, that's when we intersect again. That's when we intersect the line. So that was the other intersection point, which is smaller than 1.14. And then it stays underneath for the rest of the line. So these are the solutions to the inequality. And as you can see, this is a typical section B question. What makes it hard is not really the individual sub-questions. It's that it just keeps going on and asking for more things. And the way to do well is to not give up and run out of energy. Anyway, let's move on to question 12 and to a new formula booklet. So I raise my hand and I ask for another answer booklet. Write my name nicely. For you, you're going to have to, at the exam, know your candidate session number and fill that in as well. And of course, you'll want to fill in your full name, just to be sure. And we are solving question 12. So in question 12, we get a line in 3 dimensions given by a vector equation, and then we're given another line by another vector equation. And question A says we have to show that the lines intersect at a point A, and we have to find the position vector of A. So how do vector equations work? Well, the idea is that you imagine putting in different values of s into this calculation, and you're calculating different points on the first line. And same goes for the other one. This calculates points on the other line. And you want to calculate the same point with one value of s in this one and a different value of t. Doesn't have to be the same as s, but then this one has to calculate the same point. So we are just saying, when does r1 actually equal r2? And writing the vectors, we just put them together, we get 1 plus 2s and 2 plus 3s and minus 3 plus 6s. And I want that to be the same as the r2, which is 9 plus 40, 9 plus t, and 11 plus 2t. And when two vectors are the same, all coordinates match up. So in fact, we have 3 equations here with only 2 unknown variables, which also matches that very often you'll find that there are no solutions because there are too many equations, which matches the spatial intuition that 2 random lines in space, they rarely intersect. But we have to show that these actually do. So we just solve the 3 equations to see if we can find values of s and t. And if you like, you could do this the matrix way. Why don't we? No, I don't want to do that because it's too cumbersome. So we just take the first equation. 1 plus 2s equals 9 plus 4t, and I'll isolate s by subtracting 1 and dividing by 2. Then I get s is equal to, so first I get 8 and I divide by 2, I get 4, and 4t divided with 2 is 2t. So that's the value of s. Then I put this into the second equation. 2 plus 3s equals 9 plus t, and I substitute s. So it says 2 plus 3 times the stuff from here. That's 12 plus 6t equals 9 plus t. And sorry, not plus. I said equals. And then we subtract, let's subtract t. We get 5t on the left side, and we get 7, and I subtract 12, then I get minus 5, and the solution is that t equals minus 1. And then I substitute this back. I get the value of s is 4 minus 2 is 2. And we're tempted to just say, well, I just found s and t, but we're not sure that this is actually a solution to the last equation. So the third equation, minus 3 plus 6s, with the value of s that we just found, is equal to minus 3 plus 12, which is 9, and 11 plus 2t is equal to 11 minus 2, which is also 9. So all 3 equations are fulfilled, meaning we get an intersection point, and the intersection point, we can get that by taking either the value of s and putting into the R1, or the value of t and putting into the R2. It's going to give us the exact same result. That's what we just made sure of. So we could just say we take R1 of the value of s, that is 2. So it goes like this. 1 plus 2 times 2, that's 4. 2 plus 3 times 2, that's 6. And minus 3 plus 12 is 5, 8, and 9. And this is the position vector of the intersection. Question B. Let's see. We're still in question 12, but now sub-question B is confusing at first, because that's actually what makes this sub-question difficult, is that it says verify that the 2 lines we just worked with both lie in the plane called capital pi, given by, and then comes an equation that's quite weird. It says that r, which we haven't heard of yet, so we imagine r is some arbitrary random vector with an x-coordinate, y-coordinate, and z-coordinate, dot scalar product with this vector equals 7. And this is not the usual form of the equation of a plane. But if you think carefully that r is x, y, and z, and you also think how's the dot product made, then you can sort of read the left-hand side as x multiplied with 0 plus, because that's how you do a dot product, y multiplied with 2 minus z equals 7. And then it suddenly looks a lot like the ordinary equation for a line. Sorry, for a plane. So it is actually an equation for a plane. And that's the sort of thing that you need to stop, and you'll spend valuable minutes trying to just get rid of the confusion. But how do you show that each of the lines lie inside a plane? Well, in that case, all the points on the line need to fulfill the equation of the plane. And the minute you think that, then you kind of get the method, which turns out to be super, super simple. So it just means that we have to take one at a time the vector that creates points on the first line and check if that vector works as the vector r. So the dot product with this vector has to be 7. So let's check. So for L, we just check if r1 dot 0, 2 minus 1 would be 7. So let's just calculate it. R1 is, as we worked with before, 1 plus 2s, 2 plus 3s, and minus 3 plus 6s, and we make the dot product with 0, 2, minus 1, which means that the x-coordinates just become 0, then the y-coordinates becomes 2 times the y-coordinate, so that's 4 plus 6s, and then we subtract, so plus, and we could say minus 1 times minus 3 plus 6s. And what is that? Well, the 6s and the minus 1 times 6s cancel out. So what do we get? We get 4 plus 3, which is surprisingly 7. So the line L fulfills the equation. We do the same for the line M. We take R2 and we make the dot product with 0, 2, minus 1. This time R2 is 9 plus 4 times t, 9 plus t, and 11 plus 2t. And we make the dot product with 0, 2, minus 1. And what do we get? We get 0, because it's 0 times the x-coordinate, plus 2 times the y-coordinate, that's 18 plus 2t, and then plus minus 1 times 11 plus 2t. And what is that? Well, the 2t and the minus 2t cancel out, and we get 18 plus minus 11, so minus 11, and what do you know? It's equal to 7. So we have verified that both lines, every single point on each of the two lines, fulfill the equation that the dot product with this vector is 7. So there we go. Question C says that now we get point B that has a position vector, and a line through B is perpendicular to the plane pi, intersects the plane pi at a point C, and we have to find the position vector of C. So we have a line that goes through this point. So this is a position vector of a point, and the line is perpendicular to the plane. So here we have to realize that if you're perpendicular to the plane, then you have a direction that is given by a normal vector to the plane. So if we go back to the equation that we were given up here, we realize that the guy here, this guy, is actually the normal vector, because when we write out the equation for the plane, the numbers we multiply on x, y, and z are actually the coordinates of a normal vector. So we have a normal vector to capital Pi, and it's actually this guy 0, 2, minus 1. And we are going to use that as a direction vector for a line. So the line it doesn't have a name, so we're just going to call it the line, has a vector equation that is -3, 12, and 2, plus a parameter. We've already used s and t, so why not use u times 0, 2, -1. And this line intersects the plane at a point C, and we have to find the position vector of C. So what do? Well, we take this vector equation and we put it in to the equation of the plane to see which value of u gives us a point. So intersection with pi happens when -3, 12, 2 plus 0u, so I'm not going to write that, but here plus 2 times u, and here minus u, dot 0, 2, -1 has to be equal to 7. Or writing out the dot product, 2 times 12 plus 2u, that's 24, plus 4u, and then minus 2 and minus u, that's plus u, equals 7. And what's that? Well, that's 5u equals 7. We add 2, that's 9, and we subtract 24. So that's -15, meaning that u has to be -3. And how to get the position vector of the intersection point? Well, that's the value of u that we need to put into the vector equation of the line to get the point. So again, you can't really do this when you're working, but I'm cheating and writing down here that because it's easier for you to work on 2 pages simultaneously. So I am writing down here that the position vector of C was the name of the intersection point, so we just do that by putting -3 in as u. So we take -3, 12, 2, and we subtract 3 times 0, 2, -1, and that's going to be -3, and then 12 minus 6, that's 6, and then 2 plus 3, that's 5. There we go. And that was actually question C1. Moving to a new page, still question 12, and now answering C2. We have to find the length of the vector BC. So the vector BC is just, well, the way to calculate it is to take the position vector of C that we just found and subtract the position vector of B that we have from before. So what we're doing is taking -3, I have it written down right here, 6 and 5, and subtracting OB, which was -3, 12, and 2. And what do we get? It is 0. So -3 plus 3, and 6 minus 12, that's -6, and 5 minus 2, that's 3. And the length of BC, that's just calling up Pythagoras, saying it's the square root of the sum of the squares of all the coordinates. And 0 squared is nice, so it's 36 plus 9, so that is the square root of 45. And since this is paper 2, we might actually call up the calculator for the first time in this question and say 45 to the 1/2. That's approximately, oh, my computer is dying. approximately 6.71. 3 significant figures. Finally, question D is probably the most confusing part of this video, because then it says something that we haven't practiced a lot. I think we've had one single question in the book that was somewhat similar, but it says to find the reflection of the point B in the plane pi. And people like me get very challenged by this because I do not have a very good inner three-dimensional coordinate system. I know that almost half of all people I meet have a much better way of visualizing 3 dimensions inside their head. So for me, it's quite difficult to imagine. So I'm going to try and draw it for you. And some of you will just laugh at this and say, well, of course, but we imagine that the plane lies somewhere 3-dimensionally, and we have the point B that we were given, and we just, so notice what we just did. We found a line that goes through B and goes perpendicularly onto the plane, and we found this intersection point C. This is the work we've just done. And what do they mean with finding the reflection of the point B in the plane? Well, it can only mean one thing. It means that we have to continue to the other side of the plane and go down here and finding B prime. But once you sort of visualize this in your head, we can see that this vector from B to C is the one we found up here. So we start realizing that we've kind of done all the work already, because we have this vector BC. And how am I going to get hold of the point down here? Well, if I start at point B and then I subtract 2 times this vector BC, then I'll get this vector, this point. So I'm going to say that OB prime, the vector from the origin to B prime, we can get that by taking the position vector of B and then adding 2 times the BC vector. And that is very, very straightforward, because OB was -3, 12, 2 again, and then we're just going to add 2 times this guy, 0, -12, 6. And what's that? Well, it's -3, 0, and 8. And that is the position vector of the reflection. So since they ask for the reflection of the point B, well, they are kind of asking for a point and not the position vector of the point. So it would be nice to say the point B prime is actually in the coordinates -3, 0, and 8. I don't think you would lose any points by just making this your final result, but there it is, the reflection point. It was shockingly easy to actually do, just multiply a vector by 2 and add another vector, but realizing that this was a way to do it is hard. I guess there are also different ways, but you only need one way. That's it for this very long video. Notice that it took quite a lot more than 50 minutes. I hope you'll excuse it by thinking that my typing on the calculator is so clumsy and slow that you might very easily be able to do that part a lot faster when you're at the exam.